All right, hello everybody. Here we are post midterm 1, starting on module 3, beginning with some recursion stuff here. So recursion we're going to use a lot, like sort of going forward. So we'll sort of like go over the the intro to it here, and then we'll apply it to some problems later on here. My voice is still a little bit messed up from being sick, but it's a lot better than it was. Okay, this is recursion is like a problem solving technique, a way to sort of like write functions to solve problems that involve breaking a problem down into smaller subproblems, and you're like, big deal, that's just what functions are, right? But for recursion, we want the subproblems to have the same kind of like shape or form as the original problem. There's kind of like an old computer science like joke that is basically, if you want to understand recursion, you have to first understand recursion. And that's kind of like a joke almost on two levels there. So like one, recursion is about like sort of, defining problems in terms of themselves. But it's also a joke because it won't make any sense to you until you understand recursion. So not only do you need recursion to understand recursion, you need to understand recursion in order to understand the joke about recursion. All right, let's get into it here, right? So let's say that we want to just write a function called count, right? Count like that. And we want to pass it an int parameter, and n like that, and it's just going to print the numbers from n down to 1. So if we call count 5, it should print out 5, 4, 3, 2, 1. And then we'll say like if you give it a number that's like less than or equal to 0, it just doesn't print anything. So just to sort of handle all the possible cases, we'll say that's what that does. Now obviously you could do this with a loop. That would be sort of easy, right? So like our function takes a parameter n, and then we just loop from n down to 1, decrementing I each time, and we print out sort of each I there like that. And notice that like this handles the case where n is negative, right? So like let's say that we plug in like -2, right? Like that, right? So that means I starts out as -2. Is -2 greater than or equal to 1? This is false immediately. So that means the loop doesn't run at all, and it doesn't like print anything. So this correctly handles the case of negative numbers, even though we didn't like explicitly say, oh, if n is less than or equal to 0, blah, 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 like that, right? Like the loop handles that sort of for us there. In fact, if you want to, you don't even need the variable I. You could just decrement n, right? So we could just say, okay, n is the thing that we're starting at there like that. As long as n is greater than or equal to 1, just decrement n and then print n out itself there like that. If there was a reference on n, right, like that, we wouldn't want to do this because then decrementing n would actually be affecting the original int that is somewhere else in the program. But as long as there isn't a reference there, this is perfectly safe, right? This n here is a copy of some other int that exists in some other part of the program here. Modifying the copy doesn't change the original there like that. So both of these would do the exact same thing. But let's say we don't want to use a loop, right? So the other alternative is we could do a recursive definition. So to do that, we have to figure out how to break the problem that we're trying to solve. So the problem we're trying to solve is we're going to print the numbers from n down to 1. We want to break that down into a smaller problem, but we want it to still have the same like sort of shape or like form as the original problem here. So this is the shape of the problem. The shape of the problem is print the numbers from something, some starting point, right, down to 1, like that. So what we're doing is we're going to use the smaller problem of, okay, let's print the numbers from n minus 1 down to 1. Like that's the same shape as the original, right? It's still print the numbers from something down to 1, but it is smaller than the original because n minus 1 is closer to 1 than the original n there. So this is going to be our sort of breakdown here, right? We want to print the numbers from n down to 1. So first we're going to print n, and then we're going to print everything else. Print all the other numbers from n minus 1 down to 1 there like that. So this step 2 here is basically saying, okay, just reapply this exact same definition to solving the sort of sub-problem there. Now, if we just keep subtracting over and over and over, right, like we'll basically never stop. So then we need to know what is our stopping point. Like where do we sort of end the process and we no longer need to break the problem down? What is the smallest n that we need to worry about? And so we said that if n is less than or equal to 0, we don't print anything. So n less than or equal to 0, that's going to be called our base case. That's the point where we don't have to do any work, we're just sort of done there. That's the simplest or the smallest form of the problem. So then we have this recursive definition of our count function here. If n is less than or equal to 0, we're done. Like, that's just it, right? We don't need to do anything. We're just sort of finished there like that. Otherwise, if n is greater than 0, we're going to print n, and then we're going to print all the numbers from n minus 1 down to 1 there like that. Like, just, okay, do the whole thing again, but start at n minus 1 like that. So step 2, again, refers back to this exact same definition, just using a different n there. And that translates into code pretty directly, right? The first bullet point up here is just, okay, if n is less than or equal to 0, return. And then the rest of this is just an else off of that. So to print n, that's just a cout, obviously. Sorry, that's my ice machine over here, like that. And then this part here, bullet point number 2, right? That's just, okay, call the very same function that we're writing there. This works. Like, this is not pseudocode. I'm not just being like, oh, wouldn't it be nice if this worked or something like that right there. Like, this is actual real working C++. You can type this up and call it from your main function, and it will do exactly the same thing as the loop-based version there. So if you've never seen this before, it might seem like kind of mysterious, right? Like the function is calling itself. This isn't some other count function that we're calling here. When I say count n minus 1, I'm literally calling this function up here. And what's more, like, I'm not even done writing the function yet, right? Like, I'm still in the process of writing the count function when I write the function call where count calls itself there. So how can a function call itself? Like, how could that possibly work? Well, to sort of develop an intuition, we'll dig into like how this really works in a little bit here, but we're going to draw the recursion tree, which is kind of like a picture of what happens when we run the count function or any recursive function for its particular parameter here. So we're going to call the count function with n equal to 5 and sort of see like what happens here. So when I call count 5, that calls count 4. But it also prints 5. Sorry, let me back up a step here, right? When we call sort of count n minus 1, before we do that, we print 5. We do the cout for 5, so 5 appears over there. Then it drops into the count of n minus 1, so n minus 1 is 4. But then the same thing happens here, right? Before we go into the count 3, we're going to print 4, so the 4 appears there. Right, like that. And then we call count 3. So the process repeats. Count 3 is going to print the 3 and then call count 2. Count 2 is going to print 2 and then call count 1. Count 1 is going to print 1 and then call count 0. Now what happens when we hit count 0? We hit the first part of the if that says nothing to do, just return. Now, are we done yet? Not quite. Like, we're done printing, that is true, but the functions are not done because I'm way down here inside of count 0 and I started up here inside of count 5. All of these functions have to return their way out here. So that returns, that returns, that returns, that returns, that returns, and now we're done. Now we're back up here at the sort of original level there like that. If I have, a bunch of function calls going down, I have to have that many returns to get my way out. I can't just sort of like magically jump from the sort of bottom level all the way back up to the top there. Or actually, we'll see that sometimes we can do that, but it's a thing that like sort of happens in the background. We don't make it happen explicitly. So this works because functions use a stack to track like what are we doing right now. Like function calls are like tasks that we're performing. When a function calls another function, it's like a subtask there like that. So if we have a program that looks like this, where I have 3 functions, my main, an f, and a g, right? Main calls f calls g, like that right here. When we're down here in the sort of guts of g, the stack looks like this thing over here. So main was on the stack originally. When main calls f, that pushes f. When f calls g, that pushes g there like that. Now when g returns, that's going to pop g's record off the stack here. Let's see if I can draw over this here like this, right? So then g is going to be gone there like that, and we'll be back inside of f. When f returns, that's going to pop f's record off and we'll be back inside of main there. So like we go down, things get pushed onto the stack there, but then there's a big pile of things on the stack. To get out, we have to pop all those things off. All those things have to sort of be returned from there. So a function call pushes a thing onto the stack that is called an activation record. Oops, sorry, I made my pen all thick there, like that. An activation record. And that has information about, like, what are the local variables, like what is n, and also like just where are we inside of the function, like what line of code or whatever is executing inside of the function there. When a function returns, we pop that record off there, and then whatever is on top of the stack is always the currently running function. So when something is popped off, we immediately resume the function below it there, like that. So we can trace through the evolution of the stack while the recursion is running here. So I'm going to do the same thing we did before for count, but I'm going to use count 3 just so that it's not like quite so in depth here like that. So this should print 3, 2, 1, right? I'm only going to do this for this one example here because it's pretty sort of like detailed to sort of do this, but hopefully you'll get like the picture of how this is working. Okay, so main has its activation record on the stack. And this is assuming that we just ran this program here. So main is at line number 2. Main just started there like that. So main is starting up, and it moves on to line number 3 in count 3 here. So that main calls count 3, and that's going to push a record for count 3 onto the stack here. So whatever is on top of the stack, that is the currently running function. So main down here is kind of paused, right? It's just sort of like hanging out like that. The top of the stack is count. Count begins here at the opening curly brace. So now the CPU is running the count function with n equal to 3 there like that. So we go through the code inside of the count function. Line 8 is n less than or equal to 0. No, it's not, right? So we jump into the else. So we're going to print 3. So we'll get a 3 on our output, like that right there. And then we go into the recursion for 3 minus 1, which is count 2. So that's going to push another record onto the stack here. So notice that there are multiple n's floating around at this point here. We have the original n, which is equal to 3, but we also have this new n, which is equal to 2 here. There's multiple copies of the count function running at the same time here, although all of the ones except for the top one are kind of paused. Okay, so now like this new version of count 2 starts up. It checks to see if 2 is less than or equal to 0. That's false. So then we're going to print 2. So now our output looks like 3, 2. The 2 just got printed. And then we're going to go into 2 minus 1, which is 1. So we're going to do another count on the stack here. So that one starts up here. So now there's 3 n's floating around on the stack for all the different versions of the count function that we've sort of seen here like that. So this version of count starts up. Is 1 less than 0. Remember, n is 1 in this case here. That's false. So we're going to print 1. So now we have 3, 2, 1 on our output. And then we call count 0, which pushes another record for that. So now we have 4 different versions of count on the stack here. This one finally has n equal to 0. We check to see is n equal to 0, and then we return. So when we return, that's going to pop this record, the top record, off the stack there like that. Now when we pop that off, that resumes the count with n equals 1. But it resumes right here immediately after the sort of, this function call right there like that. So it just, is like, okay, close curly brace, we're at the end of the function. So count 1 is going to return as well, popping it off. And then same thing for count 2, and then same thing for count 3, and then we're back up here inside of main, right? We resume main, but this is the only function call inside of main, so now we're at the curly brace that marks the end of main. Main gets popped off, and we return there like that. So in terms of like the memory usage of a recursive function, you might notice a difference between the version with the loop and the recursive version here. So at our maximum level, like when we were down there in count 0, our function call stack had 4 count records on it there. So those use memory. Like the answer to this question here is, do those use memory? Is yes. Yes, they do. So a recursive function will use memory proportional to the maximum height of its stack. So like the number of records that get pushed onto the stack at the sort of like the deepest point there like that, those all get multiplied by whatever sort of the normal memory usage there like that. So the memory usage of our count function would in fact be O of n in this case, with an exception that we're going to talk about in a little bit here like that. So that's a slight disadvantage, right? The loop clearly uses O of 1. This one uses O of n, but it's not even obvious that it's using O of n there like that. You have to kind of dig into it to see like that it has that sort of memory usage there like that. If you turn on optimizations, then the compiler will probably like eliminate the extra memory for you there. So we'll talk about that in a little bit, but it's something to sort of bear in mind here. Normally we won't take problems that are easily solved with loops and solve them with recursion. What we'll do is we'll take problems that no loop can solve and solve them with recursion. So we'll apply recursion to places where it's like we don't have any choice. So it's not like we're choosing like, oh, do I want to waste a bunch of memory on this? It's like that's the only way to solve the problem. All right, let's say we want to modify this. We want to count up now. So instead of counting 5, 4, 3, 2, 1, we want to count 1, 2, 3, 4, 5. So of course in the loop, all you do is change it to go from 1 to n and increment, and that's sort of easy enough that. But how do we change the recursive version to do this? So again, we're going to frame the problem in terms of a smaller subproblem here. So our subproblem is print the numbers from 1 up to something, right? Instead of printing them from something down to 1, we're saying print them from 1 up to something here. So again, like the smaller subproblem is just n minus 1. We'll print the numbers from 1 up to n minus 1 there like that. So then we'll have this algorithm. We want to print the numbers from 1 to n. So first we're going to print all the numbers up to just before n. So if you want to print the numbers from 1 to 5, I'll sort of assign some magical recursion fairy the job of printing the numbers from 1 to 4. And then at the end, once it's done, I'll just print the number 5 there at the end. Just like before, if you give me an n that is less than or equal to 0, we don't print anything. We just return at that point. So that leads to this version of the function. And notice that the only change here really is I swapped these two lines. Like, yeah, I renamed the function, but like, we could have kept the original function name as count there like that. All I did was I switched the line where we call the function and the line where we do the printing. I just flipped the order of those two lines there like that. Everything else about it is exactly the same there like that. So let's draw the recursion tree and see how this works here, right? So remember that like in terms of what the function looks like, it's recursive call first, then printing after that here. So we're going to go down and then we're going to print here. So count up 5. Calls count up 4 and doesn't print anything yet, right? We're not going to print anything because there's no returns yet. I draw the returns in blue arrows. I haven't drawn any blue arrows yet there. Count up 4 calls count up 3. Count up 3 calls count up 2. Count up 2 calls count up 1. Count up 1 calls count up 0. And then we have hit the first part of that if, where it's like, oh, if it's less than or equal to 0, print nothing and return. Now while we're returning, when count up 0 returns to count up 1. After that returns, we're going to print the number 1. So that prints a 1 there. When count up 1 returns to count up 2, it prints the number 2. So that appears there. When 2 returns to 3, we print 3. When 3 returns to 4, we print 4. And then finally, when 4 returns to 5, we print 5. And then we are finished there like that. So just flipping the order of those two lines reverses the order that the numbers appear in the output there like that. If I do the printing first, I count down. If I do the printing after the function call, I count up. The point where the function calls itself, that is called the recursive function call. So any code that you put before that is going to happen like while we're sort of working our way down there. It's going to happen in the sort of normal order. If you start at 5 and you go down to 1, that's going to happen in the order of 5, 4, 3, 2, 1. But any code that you put after the recursive function call is going to happen on the way up. And because it's using a stack, right, stuff on the stack gets popped off in the reverse of the order that they were pushed on. Those things appear to happen in reverse order. So the recursive calls themselves, like if we sort of draw the picture, it goes 5, 4, 3, 2, 1, 0, but the numbers are printed in the order 1, 2, 3, 4, 5 because the cout statement is after the recursive call. It happens while the stack is popping stuff off there. There's a few elements that every recursive function has to have here. So we have to have at least one base case, and that's the simplest or the smallest form of the problem where we can give an answer without any extra work. So no recursion needed here. So that's our n less than or equal to 0. We just return in that case here. Sometimes there'll be more than one base case, more than one simplest form of the problem, but here there's just one here. And then we need to have at least one recursive case, which is everything other than the base cases, things where the problem is bigger than that, and we break it down into sort of sub-problems here. So here our recursive case is the whole sort of else part of the if there like that. Again, sometimes we'll have more than one recursive case, more than one way of breaking the problem down. We'll see an example of that later on, but this one only has the one there. And then you can identify the recursive case because it has the place inside it where the function calls itself, and that is called the recursive function call. If you don't have a recursive function call, then you don't have a recursive function. So clearly you don't have a recursive function case there like that. Some recursive functions will have more than one function call inside them, more than one point at which they call themselves, but this one only has one there. Now let's do something different. Let's make a recursive function that returns something. So not printing something, but returning a value here. So we want to write a function that sums up the numbers between 1 and n, like integers here, like that. So our sum function is just going to compute this sum of 1 plus 2 plus blah, 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 plus n minus 1 plus n. We saw in the analysis section there is a nice closed form solution for that. It's just n times n plus 1 over 2, but we're going to do the summation explicitly. Now, of course, you could use a loop, right? You would have a variable for a running sum. That's our s here, right? So that's our running sum, like that. And then we just make our variable I count from 0 up to n, and then each I we see gets added into s, and then we return s when we're done there, like that. And of course, just like we did with the count function, we don't actually need I here. You could write this just in terms of n, so you could say for no initialization, n greater than or equal to 1, decrement n, s plus equals n. Right? Because it's a sum, so it doesn't matter whether you do it as 1 plus 2 plus 3 plus 4 or 5 plus 4 plus 3 plus 2 plus 1. The order in which we do the summation doesn't matter there like that. So either of those would work for a loop. But we want to use recursion, right? We're not in loop land. We want to use recursion here. So we're going to reformulate our problem into a smaller problem of the same form. And that form is add up the numbers from 1 to something. So our original problem is add up the numbers from 1 to n. And we want to kind of look at that and say, where inside of that can I find a smaller problem that still has that kind of same shape? And the answer is, of course, right here. If we add up the numbers from 1 to n minus 1, that's the same kind of problem. You can still phrase it in terms of add up the numbers from 1 to something. But in terms of the size of the problem, the number of things that we're needing to add up, there's one less thing in the summation there. So that's going to be our sort of smaller version there. So we're leaving out the final plus n term at the end there. So I can write that as, okay, add up the numbers from 1 to n minus 1, and then add in the missing n at the end there. We need a base case. So our base case is just if you ask me to add up the numbers from 0 to 0, you just get a 0 there like that, right? Technically, we'll make this base case be if n is less than or equal to 0, just so that we cover all the possible values here. So here is our recursive implementation of that. Right there. If n is less than or equal to 0, return 0. Otherwise, we say, all right, magical recursion fairy, go add up all the numbers up to n minus 1, and then I'll just do the last step. I'll add in the missing n there like that. Oops, sorry, let me label this here with the sort of elements of this. I thought I did that in the slideshow, but I guess I didn't. So where's the base case? The base case is the first part of the if right here, where we don't need to do any extra work. So that is our base case, right? Which means that the else part of it is the recursive case, where we break down the problem into smaller bits and pieces there like that, right? And then where is the recursive function call? The recursive function call is that thing right there. The point where the function calls itself, that's the recursive function call. So that's our sort of annotation of this version here, like that. Okay, so let's draw the recursion tree and see how the returning part of this works out. So sum5 calls sum4, but then it sort of remembers like, oh, on the way up, I need to add a 5 into whatever that returns here. So when sum4 returns, we're going to do this sort of addition of the plus 5 there, like that. Sum4 turns into sum3, but it sort of saves away on the stack the fact that it needs to do a plus 4 after the sum3 returns here. And then we just keep sort of going down, like these things over here, these additions, that's our to-do list of stuff that needs to happen while we're returning here. Like a stack is like a to-do list. This is our to-do list of things we need to do later on here. 2 turns into sum1, 1 turns into sum0, and then sum0 gives me a 0. So this is my base case down here. Right? We're not doing any recursion, we're just going to return a 0 there. So then we return a 0, so on the way up, you can think of it as like this function call here, that gets replaced with the return value, which is 0. So that becomes 0 plus 1, which is 1. And then that 1 works its way up here. So this is going to get replaced by 1. So this becomes 1 plus 2, which is 3. That 3 replaces this, right? So this translates into 3 plus 3 is 6, like that. Then 6 replaces this, so this becomes 6 plus 4 is 10, like that. And then finally, this 10 is going to replace that recursive function call there. 10 plus 5 is 15, and then 15 is the answer to the original summation there. So on the way down, all we're really doing is subtracting 1, right? We're just decrementing, counting down until we hit 0. All the real work here, all the actual additions happen on the way up as the function is returning, as we're popping stuff off the stack. Let's do another one, right? So Fibonacci sequence here, right? This is kind of a fun math thing here. Like, I think a lot of us, I don't know, it depends on what kind of school you go to. I learned about this in like elementary school, probably because the teacher was just like, oh, I can give this to kids and then they'll just, you know, try to make the Fibonacci sequence out like as far as they can go, and it just like keep us busy. But you know, you learned about this at some point here. So the sort of the Fibonacci sequence is defined by just two simple rules. We're going to start with 1 and 1. Like, so the first two elements are always 1 and 1 there. If you want to be kind of fiddly, technically you can start with any two elements there, but usually it starts with 1 and 1. That's the traditional form there. And then all the later elements of the sequence are formed just by adding up the previous two elements here. So for example, over here we start with 1 and 1, right? If you do 1 plus 1, you get 2. Then the next one here is going to be 1 plus 2. So grab the previous two elements there. That gives me this sum, gives me 3. Just going through all my colors here, right? The next one is going to be 2 plus 3. So grab those two elements, 2 plus 3. That gives you 5. The next one is going to be 3 plus 5. That's going to be 3 plus 5 gives me 8. And so forth. So for any particular element, right, if I sort of like fast forward down here, like 34 is going to be the sum of the previous two elements there, like that. You can see how, like, you know, for kids who just learned how to do addition, like sort of grinding through this is something that could be like a little bit sort of fun. I don't know, for certain definitions of fun, I guess. So mathematically, the Fibonacci sequence is nice for our purposes here because it's defined as a recurrence relation, which means it's already comes to us in a recursive form here. So F0 and F1 are just defined to be 1. That's going to be our base case. Like that. And then Fn is defined in terms of n minus 1 and n minus 2, the previous ones. That's going to be our recursive case there, like that. So we don't have to do any work to figure out how to do this recursively because it already sort of comes to us defined that way there, which is kind of nice. So here's our pretty easy sort of definition here, right? We have two base cases, n equals 0 and n equals 1. Take that right there. You could, of course, if you wanted to group those together just with like an or, so you could say like, you know, if n equals 0 or n equals 1. It would still be 2 base cases, but in code it would only be like, one branch of the if there like that, right? And then we have a recursive case down here. And inside of our recursive case, we have 2 recursive function calls, whereas previously we've only had 1. And that's going to have a sort of like a big effect on how this function works. Right, 2 recursive function calls here. So let's draw the recursion tree for this here, right? If I was doing this like in person on the board, this would take me like 15 minutes, and I would always like screw it up and not leave myself enough space on the board. But fortunately for you, I've sort of like pre-written this out here, so it'll just kind of like go nice and easy. So we do fib of 5, and that is going to be 5 is right greater than 1. So we're going to recursively break this down into 5 minus 1, which is 4, and 5 minus 2, which is 3. So this splits the recursion tree into 2 recursive function calls here, fib4 and fib3. But then each of those splits into as well, right? Fib4 splits into 3 and 2, fib3 splits into 2 and 1. Now, functions don't remember anything about previous times that they've been called here. So it's not like, oh, the fib function computes fib of 3 once, and then over here it just uses that sort of same return value. Every time we call fib of 3, it's going to recompute what fib of 3 is here. Fib of 3 splits into 2 and 1, fib of 2 splits into 1 and 0, fib of 2 splits into 1 and 0, and then fib of 1 is actually at a base case, right? This last one over here is one of our base cases there like that. And then all of these 1s and 0s are base cases except for the fib of 2 over there, which still needs to split into 1 and 0. So now we have all of our sort of base cases here like this. But we're not done, right? Because all these additions have been piling up on the stack, waiting to be performed. They can't be performed until we get like the sort of base cases that tell us what is on the left and right hand sides of the addition. So now we can start working our way back up and doing those there. So what's 1 plus 1? That is 2. So the answer to this is like 2, right, like that. Let me see if I can match the color there a little bit better, right? So 1 plus 1 is 2. Then this over here, this is like 1, this is 1, this is 1, this is 1, this is 1, right, like that, right? So then all of these are, this one here is 2, this one here is 1, 1, 1, 1, 1. So this one here is 2 plus 1, this one here is 1 plus 1, this one here is 1 plus 1. So that means up here we have, this one is 3, right? And then this one is 2. This one is 2, like that. This one is 1, right? So now we're going to do these, right? So this is 3 plus 2. This is 2 plus 1. So then now this one is 5, right? And then this one over here is 3. So then we'll do 5 plus 3, and we certainly get 15. That's not right. Is that right? Did I screw it up here somewhere? Let me rewind the tape. Back here. No, it should be 8. I don't know where the 15 is left over. Haha, from when I did the count one there. Sorry about that. Okay, so that's scribble that out right. That should be 8. Sorry about that there, like that. I don't think 15 even is a Fibonacci number, is it? That might be an interesting, like if you want a problem, if you want a puzzle to sort of work out, figure out what 2 numbers you could start the Fibonacci sequence at so that 15 shows up somewhere in the sequence. Like consider that your sort of challenge there like that. Now, one other thing to sort of note about the way that I drew this here is the computer can't actually run more than one function at the time here. So I've kind of drawn this as if fib of 4 and fib of 3 happen at the same time, and fib of 3 and fib of 2 and fib of 2 and fib of 1 all happen at the same time. That's not actually the way that it works here. So the way that this works is the CPU will sort of say, okay, fib of 5, I need to do fib of 4, and then it'll sort of remember, oh, later I need to do fib of 3. And then fib of 3, it'll be like, oh, I need to do fib of 4, I need to do fib of 3, fib of 3, I need to do fib of 2, fib of 2, I need to do fib of 1, and then it'll hit its base case there. And then, so it can only really do one of these at a time. It will still explore the entire sort of tree, but it'll do it like hitting one function at a time there, like that. The animation would just take forever if I had actually done that, but like that's kind of how it works in the real world there. So functions like fib are a little bit different, right? The tree looks different than when we did like the count or the sum functions here. They are called non-linearly recursive. Their recursion trees branch out rather than just going like sort of straight down and straight up there. So our categories of recursive functions are, we have linearly recursive and non-linearly recursive. So a function with one recursive function call per recursive case is linearly recursive. It's going to look like a straight down, and then maybe some stuff happens on the way up there like that. Non-linearly recursive is going to branch out, right? It's going to sort of like fan out as we work our way down, because each recursive call is going to split into more than one thing, and then those are going to split into more than one thing, and then those are going to split into more than one thing, so it branches out like that right there. A subcase of linearly recursive functions are tail recursive functions, and those are ones where we go down, but then we don't need to do anything special on the way up here, like nothing happens on the way up. So the compiler may be able to optimize that by just jumping straight up to the top there like that. Linearly recursive functions correspond sort of loosely to like loops, right? That's what we started out was we started with a loop and then translated it into a recursive function here. The tail recursive functions correspond exactly to loops here. Any loop can be directly translated into a tail recursive function. Any tail recursive function can be directly translated into a single loop there like that. So they kind of like are like one-to-one. Non-linearly recursive functions don't correspond to loops. There are actual real problems that you can solve with a non-linearly recursive function that you can't be solving with loops there. So that's the interesting part of recursion, right? Is like, what are these problems where I have to use recursion? I can't just sort of like write a loop to solve it there. Tail recursive functions, these are the ones where we don't do any work on the way up here. So remember, like our sort of structure is if we have a recursive function f, right? When we have the recursive function call f inside of it there like that, anything that is above that is going to happen on the way down. So we're like, okay, working our way down the recursive tree there like that. And then anything after the recursive function call happens in the reverse order on the way up. So what the stack is doing is the stack is basically keeping track of the stuff that needs to happen on the way up there like that. That's what the stack is sort of being used for, is it's our to-do list of, oh, after I'm done doing this, what do I still need to do there? So if there is nothing after the function call there, if there's nothing that needs to happen on the way up, then the compiler may be able to optimize away that extra memory. It's sort of like say, oh, I don't actually need to save this to-do list because there's nothing on it there like that. So there are some programming languages where this is like guaranteed. If you write a tail recursive function, the compiler will sort of like eliminate the extra memory usage of the stack. That's not a requirement in C++ here. The compiler may optimize tail recursive functions to only use a constant amount of stack space there. It's still like worth doing, right? Like if you have to write a recursive function, try and see if you can do it tail recursively there. But it's not like a hard guarantee. Like you may still end up with something that is using sort of extra memory there like that. So if we compare our original count and count up functions here, which one is tail recursive? So in this one, we print n, right? Then we do the recursive function call. So that's our recursive function call there like that. And then the function returns. I've added an explicit return statement here to sort of mark where the function returns here. So there's nothing that happens between the recursive function call and the point where the function returns. So that means count is tail recursive. Right? It just goes down. All the printing happens on the way down. On the way up, all we did was just return. Whereas in count up, here is the recursive function call. That's where the function calls itself, right there. And then the return is down here. Something happens in between those two things here. It's not just recursion, return like that. So this one is not tail recursive. The stack has to keep track of all the ends that need to be printed on the way back up there. Another way to think of tail recursion is the compiler can just replace this, the point where the function calls itself, with just a jump back up here with like n equals n minus 1. So it just basically rewrites the recursion into a loop there. If there was something that happened between those two things there, that doesn't just happen once, right? It happens every single return, so I can't just sort of manually translate this into a loop there like that. I need at a minimum like 2 loops or something like that. I won't ask you to like write a tail recursive function on like a test or anything like that, but it's good to sort of know, like sort of see the process by which we turn a recursive function into a tail recursive function here. So let's look at our sum function, right? So as we've written this is not tail recursive, because here's the recursive function call, right? Before the function can return, though, it has to add n in. So the plus n here happens between the recursive function call and the point where the function returns, like that. Like it's recursive function call, we get the return value, then we do the addition, then we return out there like that. So this function is not currently tail recursive. To make it tail recursive, we have to arrange for all the work, all the like addition in this case, to happen on the way down, so that when we hit that return statement, we're just doing something like this, right? There's no return sum, blah, 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 do some other stuff, and then like return the value. It's just return whatever I'm given there like that.